Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Great. So it's my pleasure to introduce Emery Berger. Emery Berger is a professor at University of Massachusetts in Amherst. He got his PhD at the University of Texas. He's been working in the areas of performance, parallelism, concurrency, as you see in this talk today. He's also worked on security and predictability of systems. So he's got a wide range of skills, interesting ideas. You've seen him many times here before, and so I'm happy to have him speak again.
All right. Thanks, Ben. I'll add correctness and operating system stuff, and turtles. So you can go to my webpage and see what I mean. OK, so let's see. So I'm not going to bore you with this, right? So this is the whole multicore, yada, yada, yada. All right, everybody's on board, right? OK, good. All right, so it's bad, right? Why is it bad? So it's bad for a variety of reasons. For correctness, right? It's notoriously difficult to get right. You have races, you have atomicity violations, you can have deadlock, there's order violations. People are actually discovering new ways of talking about ways your program can be wrong, which is kind of fun and exciting. But of course, getting the multi-threaded program correct is really only half the battle. I mean, you don't write a multi-threaded program just to get the thing right, just to overcome these errors. Otherwise, you just wouldn't have written a multi-threaded program. So you actually do it, of course, for performance. I should say this is a little plug for some other work that addresses all of this stuff called Grace. I'm not going to talk about that much today. So you've got this multi-core rocket, and you're trying to make something fast. But if it's not fast, it just doesn't matter, right? I mean, if you have a multi-threaded program and it doesn't take advantage of your cores, then who cares? You did something wrong. All right? So how can it go wrong? So there's a bunch of ways your program can go wrong in a performance sense. So you can have too many, you can have too few threads. So too few threads means, say you have 8 cores and you have 4 threads. Clearly, you can't take advantage of all the cores. You can have too many threads. So you can have hundreds or thousands of threads. You can be spawning threads all the time. And then you pay the overhead of scheduling and context switches. And you pay the overhead also of thread startup and thread teardown. Right? So this is like a very short primer for those of you who have not had to deal with performance tuning concurrent programs. What else can happen? Well, you can have contention. So that's a lock. So if you have one big lock, you have a problem, right? Because all the threads are constantly contending for this lock. Only one can get it at a time. Only the big dog, right? So only one can get it at a time, which means everything becomes sequential. So that's no good. So solution? Lots of locks, except that's bad too, because in fact, lock acquisition and lock release is a relatively expensive process, as well as atomic updates being fairly expensive. So you can see that there's all of these issues with performance tuning concurrent code. But the good thing about all these issues is that they're sort of obvious in the code, right? So, or they're easily, they're easily exposable with existing tools, right? So if you see one big lock and you run some performance tuning thing, you'll discover, hey, there's a ton of contention on lock 12. All right? Likewise, if you have this death by small cuts, you'll see thousands and thousands of lock acquisitions. You look in your code, be like, OK, I see those locks. All right? All things that you can address. So, oh, man, that's really dark. It is appropriate, I guess. There are more insidious errors. And the insidious performance error I'm going to talk about today is false sharing. All right, so why is false sharing insidious as opposed to these others, which are just bad? So it's insidious because you can end up sharing something that you didn't really realize you were sharing. All right, so how many of you have seen the movie Brazil? Oh, man. The crowd is getting, this is bad. I'm showing my age, I guess. All of you should immediately rent/stream Brazil. It's a Terry Gilliam film. It's fantastic. Dystopia, quasi-sci-fi. This is totally up your alleys, OK? All right, you should immediately rent it. And you are culturally deprived without having rented it. But there's an amazing scene where he's put into this, so he basically joins this company and he's put in this incredibly, insanely tiny office that's like 1/12 the size of a Microsoft intern space, okay? And he gets in, he starts setting things up, he sets things on his desk, and his desk starts disappearing into the wall. And then he's, you know, that shouldn't happen. Things start falling off, so he starts pulling on it. And then you see on the other side of the wall, there's another guy sharing the same desk. And so they're both basically playing tug of war, trying to get more desk space. The problem is, right, he came in and he thought he had a desk, but in fact he was sharing it with some other guy, and he had no idea. And this is pretty much what happens with false sharing, although it's maybe less entertaining. Okay? So in false sharing, you've got, you know, the thing the dogs are fighting over, right? This is a cache line, all right? And cache lines are getting relatively large. 64 bytes or 128 bytes are reasonable cache line sizes. And you know, to sort of remind everybody of their architecture class, sharing and communication across cores/processors happens at the cache line level, right? So you don't share a byte. You don't say, I'm going to alter this byte and so on. You actually alter a whole cache line. So if I make a change to a cache line that you have in your cache, your copy gets invalidated. So this is the whole cache coherence thing. The problem occurs when I've got a piece of a cache line and you've got a piece of the same cache line. And as we make updates, secretly, performance is going to hell, because when I access my cache line, if you've already modified your piece, my piece is now invalid. So I have to go all the way down to the bus and get the thing. It's like a cache miss all the way down and then fetch it back again. So of course, this is at 1 to 2 orders of magnitude slower than the direct access that you thought you had. And every single time you make a modification, you will also have to fetch the invalidated copy all the way back. All right? So this can cause a program to silently serialize itself. So if I have a program that's doing a lot of updates to shared state with no locks, right, no visible contention, the program can actually, in effect, run at serial speed or slower, right? Because, you know, individually, these things were actually hitting in the cache in L0 all the time, and now it's missing all the way down to RAM. OK, so here are some examples. This is going to be a pretty breezy, high-level talk, by the way. So I encourage you to ask questions if you want some details, because the details are not on the slides. OK? That's what papers are for, by the way. Yes, I know. It's shocking. So this work, by the way, is in submission. It's a tech report. I'll put it on my webpage when we get back. All right. So here are some examples of ways you can get false sharing. So one of them is you have these globals. So in each of these cases, I have something and you have something. And that means I'm a thread and you're a different thread. All right. So here I make an update to this global. You make an update to this global. Surprise, globals tend to be co-located. All right. So it's not like it lays them out 64, 128 bytes apart. So 2 integers, for example, will almost certainly be laid out directly next to each other in memory, which makes it very likely they'll be on the same cache line. All right. Similarly, or perhaps a little bit more surprisingly, this can happen where 2 separate heap allocations can actually end up being co-located on the same cache line. If you use the Windows allocator, this is more or less guaranteed. And some, you know, from some point of view, this makes a lot of sense, right? I have memory. You ask for memory. I'll give you a piece. Somebody else asks for memory. I'll give them the next piece. All right. There are memory allocators, including one that I've written, that tends to avoid this, but nothing eliminates it altogether. Here is, I think, something that's more likely to happen, where you have a class. Well, I shouldn't say more likely to happen. It's something that's a little trickier to deal with. You have a class. One thread is updating one field. Another thread is updating a different field. All right? It's also the case that if you just have one big object and you share out pieces of it to different threads, then those will, of course, all be next to each other, and therefore could lead to false sharing. Finally, and this is something that was actually has been dealt with long ago in the Fortran world, is array index-based false sharing. So if, especially when you do automatic parallelization of Fortran programs, which is more or less reasonable, surprising as that may sound, because Fortran is this tremendously easy programming language for analysis point of view, if you have these arrays and it can resolve where these indices come from, or if you're parallelizing a loop, you can basically do a static analysis and get the chunks that are going to be on different threads to not end up on the same, accessing things on the same cache lines. All right, so I'm not really going to talk about arrays today. I'm just going to talk about this other stuff. Yes?
So, I mean, isn't it a matter of design? I mean, for example, if you have two threads updating adjacent fields in a record, structure, whatever, that seems like just a bad idea, right? I mean, and in Fortran, for example, the standard way you model that is you'd have two parallel arrays, right? And so each array would represent one of the records. If it's an array of structures.
Right. Yeah, it's. I mean, is it a bad design? I mean, I think that the real question is whether this is something that's obvious. And I should add that this cache line size business and the way things get laid out also means that on some architectures you won't get fault sharing, and some you will. So there are programs that used to not exhibit fault sharing because the cache line size was 32 bytes. And now 64, 128. And actually, I mean, the heap-based fault sharing is definitely an issue that's very difficult to resolve because this happens below the level of the programmer's abstraction, right? So the programmer just says new. They have no control over where the memory goes.
Also, I mean, there are mechanisms like heaps, right? You could have, in Windows, you could have a separate heap for, foo and bar.
Yeah, you could.
Right?
You could. That's right. So I would refer you to my classic 2000 paper on Horde, which discusses these issues in depth. It's a problem, right, if you have separate heaps, because the amount of memory you consume grows with the number of threads. Unless you have some way of balancing. In Windows heaps, you can't really do this. And there's another kind of fault sharing that can occur from recycling. So I don't want to go down the rabbit hole on this. But in short, if I have an object, suppose I allocate something. I'm me, you allocate something, and conveniently they're very far apart. But then you allocate a bunch of stuff and it's close together. That's good, right, on your thread. And then you pass those things to me. Then I will end up falsely sharing them with you. And this kind of thing is very difficult to deal with. All right, and I should add that coping with it at a programming language level, like for the programmer, this is dicey. You really want to the extent possible, resolve that time, if you can. All right.
It goes to the talk, though. I mean, at some level, I'm curious about your philosophy around the question of, should this all be done automatically, or should the programmer have some abstractions and be involved in the process?
So I always lean on the side of automatic.
Okay.
The programmers have it hard enough. I would rather, as programming language people, right, in theory, we should all be saying, make life easy for the programmer, make them more productive, hide the grubby details down below. Right? So that's definitely my philosophy. And I think that there are issues with portability and complexity. It's very easy to say, well, just put this here and put this here. But when you have, a very big program, this becomes difficult. All right. OK, so what happens with previous tools? So there's not much work in this area, actually, somewhat surprisingly. So one of the approaches is basically instrument every access and serialize all the threads and watch what all the threads do to every single read and write. Okay, this is, in theory, this will catch everything. It's slow.
Previous tools to do exactly what?
To detect false sharing, specifically, yes, specifically for false sharing.
Not to prevent it or
No, nothing existed to prevent it. That's a good point. All right, so this is really just the detection story. There previously was nothing to prevent false sharing except the static analysis for Fortran programs that I described earlier when you're doing auto-parallelization. One of the big issues is false positives. So when you get a ton of reports of sharing, it doesn't really know, for example, in most of these tools, if you call malloc and then you free it, and then somebody else calls malloc, it sees the same address being used by different threads. And then it will report that as sharing, when in fact it's not, right? There's no sharing happening at all. So that's the issue with instrumentation. There is a tool called PTU. Don't ask me what it stands for, performance something, from Intel. This is actually what happens on one of our test programs. You get a dump of all of the cache lines that were responsible for roughly speaking, coherence traffic. And so it does this at the address level. You get offset something, thread something, And at best, it gives you a function, which is relatively good. You get a bunch of these messages. It can't distinguish between false and true sharing either. So really, you just get a ton of stuff, and you have to sift through it and hopefully find out what happened. All right? So that's the state of the art.
So
yes?
now, what do you think? Do you think that state of the art reflects that it's a hard problem or that there's no interest in it?
OK. I think it is. It's certainly interesting. I mean, way back a long time ago, I knew, people were, there was some company that licensed Horde specifically because of the false sharing. Mm-hmm. So what happened, it was quite interesting. So as a scientific code, it was a boundary element method solver, which turned out to have lots of applications for a bunch of different sort of physics and engineering problems, right? So it would allocate a bunch of memory, and then it would churn on it. It would do a bunch of computations. It never called malloc in that section of code. So it called a bunch of mallocs, and then for the bulk of the execution time, which is a lot, it would spread it out on multiple threads and then do chug. The problem was that it was using a conventional allocator, and it had massive false sharing. So the scaling did this, so which wasn't good. And he plugged in Horde. He had no idea what his problem was. I think this is sort of the take-home message of all this false sharing stuff. Nobody knows if they have false sharing. They suspect the other things, but false sharing is this invisible performance killer that's very difficult to get a handle on. Even if you go and you plug in one of these tools, it just reports a bunch of sharing stuff. It doesn't really tell you, here's some false sharing. So I think that people have not had a good handle on even being aware of the problem, and then how on earth to track it down.
But Intel, at least ostensibly, has made a case that it's providing performance tools for concurrency, right?
Yes.
They want to improve. Yeah. They're giving you multicores. They want to make sure you're using them. So
that's right.
You'd think they'd have a vested interest in making the quality of these tools better. I mean, you can do better than this without being, without rocket science in some sense, right?
It's hard to see how, actually. I mean, I think so. This is, using performance counters.
Right.
So it has all these on-chip performance counters, but it doesn't know about malloc, right? It doesn't know about fields. It just sees cache lines. So if you operate below a certain level of abstraction, it's very difficult to know what the hell's going on. It's cheap, right? And it gathers these statistics at very low cost. But in this particular case, it's not very useful.
But they also have compiler people who work there. I mean, it's not like they,
sure, we know
they couldn't figure out how to raise these things up to more meaningful.
Look, let me put it this way. I'm going to present what I've done. There might be other ways of doing these things, but I don't know what those are yet.
Yeah, okay.
All right, especially with low overhead, which is where I'm going.
So what?
All right, so here's Sheriff, which is what I'm going to talk about today. So Sheriff has two modes. Sheriff has a detective mode, where it will find these false sharing problems. And it will report them pretty precisely. So it'll arrest the culprit. So it's, in particular, it has no false positives. I will say up front, there is the possibility of false negatives, which I can get into some detail on. But in general, it's quite good at catching these things. And when it catches something, it narrows it down to the object that was the culprit. If it's a global, it'll actually tell you X and Y are responsible for false sharing. OK. There's also a prevention mode. And the prevention mode will actually eliminate false sharing altogether, which seems like a bizarre thing. Yes. So I view this as something, this is sort of a, call in the cavalry. I don't know what to do. But it's maybe a very complicated program, and you don't want to try to use these detection mechanisms to help you find it and then fix it. You can actually, for some programs, just plug in Sheriff, and your program will run faster. But I would recommend this mostly for catastrophic cases, like OK Corral kind of situations. All right. So how does it work? So as Ben alluded, there's some magic involved. This magic is partially reuses some magic from Grace. So I'm going to talk about the Grace magic and then the new extra magic that's involved. OK. So how many of you are familiar with Grace? OK. All right. So there's enough people who are not raising their hands. So just briefly, the idea behind Grace is take a program that is concurrent, make it run without any errors. OK? That is no concurrency errors. I mean, if you say, print 12 and it should have been 13, can't help you. But no concurrency errors. And it does this through a variety of mechanisms that enforce a deterministic execution that corresponds to a serial version of your program. All right? So if you said pthread create something, then it would be as if you just synchronously called that function. That's the effect you get out of Grace. All right? And you actually can get good performance. It's specifically designed for fork join style parallelism. It was not, at least as reported, able to handle general purpose parallelism. All right? So one of the tricks that Grace relies on, so here's a multi-threaded program. I'm using the syntax which is borrowed from Silk instead of the gory pthread API or the far gorier Windows API. But here, this just means create an asynchronous thread. So f of x starts running. The result will eventually be stored into T1. Likewise with g of y and T2. And sync means wait for all the spawn threads to complete. OK? So this is a very simple multi-threaded program. What Grace will do with this, and by extension what Sheriff will do, it will actually convert these threads into processes. All right? So all of these threads will, roughly speaking, be turned into actual calls to fork in Linux. And they'll go and they'll run. Now, clearly, this doesn't make sense as I described it, because processes don't share memory. So we use mmap hackery to provide a shared image. And then in Grace, you actually keep track of which pages you've modified, and there's a sequential commit protocol for actually writing those results back into the shared space so they become visible to everybody. The beauty of doing this is that every process is totally independent. And so the changes that happen in one process are isolated from that of the other. All right, so Sheriff extends this mechanism to work for general purpose programs, that is, programs with barriers, programs with condition variables, not just fork join programs. All right, so now I'm going to go through an example of the other key mechanism of Sheriff. All right, and so what we're going to do, I'm going to use this totally stupid multi-threaded example to explain to you how it works. All right. The idea is I spawn two threads. They do nothing but write 1 into x and 2 into y over and over again. All right, it's manifestly not a real program, but it's a good example of what would really kill you with false sharing. So suppose x and y are on the same cache line. If you run these programs, they will definitely run far slower than if you just ran them in sequence, because it'll just be cache miss, cache miss, cache miss all the time. All right? OK, so that's the threaded version. In the Sheriff version, what we're going to do is we're going to run these things as separate processes. And here, I'm going to say that initially, the values of x and y were 0, just for the purposes of this example. All right? So when this thread starts running, it's going to repeatedly be writing 1 into x over and over and over again. And likewise, when this guy starts running, he'll be repeatedly writing 2 into y. Now, note, these are separate processes. So what happens with cache coherence in separate processes? Nothing. OK? Nothing. There's no cache coherence because there's no shared memory. So in fact, all of these executions happen privately. So there's no false sharing at this point. So it'll just happily run. These will all be cache hits, 1, 1, 1, 1, 1, boom, boom, boom. Same thing here. All right? So this gives you sort of a hint as how we can prevent the false sharing by using these processes. All right. So now we've done all the stuff with the processes, and it's time to commit the results. So the threads have ended. So what we do is we take this page is actually a twin. It's a copy of the page before we ever wrote it. So we use page protection, and as soon as the signal handler is triggered, copies this page and saves it off to the side. So it goes and it looks at, for every page it's written, it compares its contents to the twin, and it discovers, hey, this is different. This 1 is different from the 0. And then it just writes that value. It writes the diff into memory. OK? The same thing is going to happen here. It's going to discover that the 2 is different from the 0. And then it's going to write the 2 in. OK? So this actually, in essence, is the prevention story. So you basically run all of your regions of code essentially between lock and unlock, unlock and the next lock, any of these commit boundaries. If you want to think about it as where there be edges in a happens before relationship, that's where these boundaries are. All the writes happen locally. And then at the end of one of those things, they're all committed. Yes?
Does it assume that
Excellent observation. It does. It assumes that the program, let's put it this way. It assumes that the observed execution is race-free. All right? If it is not race-free, then it could, so if you had something making modification here, another thing making modification here to the same item, clearly one will win. So the results are just as undefined in Sheriff as they would be in a conventional multi-threaded program, with the caveat that you're more likely to see the race. So if imagine that in this program, so I have a program, say the program that this big section lasts for a week, okay? On Monday, I write x equals 1. On Tuesday, you write x equals 2. On Friday, we commit x equals 2, okay? So you will definitely get some sort of a race. And it's going to happen in a quasi-deterministic way. But we're going to assume that your execution for the purposes of this, for the tool, whether for prevention or detection, you don't observe races.
So
okay?
That doesn't invalidate any correctness guarantees because you're already starting with a semantically ambiguous program.
That's right. You're exactly right. It could nonetheless have a practical impact, because you could have a race that happens, sort of very, very rarely in the real execution, but because the effects are delayed, the race could become manifest where otherwise it would be hidden. Okay? It might be a good thing. In fact, we initially were looking at this as a way of detecting data races as well, and it does detect these data races. The problem is it just says you had a data race last week. Okay? And here's the object you had the data race on, which is it's sort of useful, but it's not really what you want. Yeah?
So how does true sharing work? I guess in this context, you have...
So true sharing is not going to appear here,
yeah.
Because when you have, in a correct program, when you have true sharing, you have a lock.
Right, okay.
Okay, so when you have a lock, at the end of the lock, the diff is committed.
Okay.
All right, and only one actually gets to do it at a time.
Okay.
Yeah.
So when you're inside a lock, only one of these things, you don't have to spawn the process, right?
Yeah, I mean, if they're actually sharing, they're sharing X over here. Yeah, no, you don't spawn any new processes.
That's
it's
right.
only when you create a
There's only
thread.
one process when you're...
There's only, every thread equals one process, not more processes. All right, so this is essentially the prevention story. Yeah?
You're doing here that the hardware couldn't do, or is
Well, the hardware is helping me.
I mean, so you're delaying merging these two different states together. So why can't the hardware just buffer the writes on each processor and also...
Yeah. I think buffering won't work. You would have to do something more like this, because what happens with buffering is that you would overflow a buffer. Right? This could last for millions or billions of writes. Right? You'll only record, the changes are happening here. Suppose it's writing, 1 to a bazillion and back over and over and over again, right? So when it does that, it'll just, constantly be making these modifications. If you buffered them, at some point you'd run out of memory. Here, the writes just happen directly.
Yeah, the memory consumption increases in the order of that number of threads.
So here it increases in the order of the number of pages modified by each thread.
When you run a process,
Yes.
all the memory.
But it's copy on write.
Okay.
So basically all of the read pages, the pages you haven't modified, are shared. There's just one copy. But as soon as you modify one, you get your own copy. That's a good question. Okay, so that's essentially the prevention story. The detection story is a very simple extension. What you do is, whenever you go to write something into memory, you look at the cache line around it. So you look at the other contents. And if the other contents differ from what you saw before, it means that there was some false sharing.
So that's Dan's favorite false negative, right? If process 1 wrote 1 to X and then wrote 0 to X again,
Yes.
you wouldn't see that.
That's exactly right. That's exactly right. So for this sort of ABA type situation, you couldn't. What should I say? If your observation is basically correct, which is the only way we're going to detect things is by a difference in value. All right? If you don't have a difference in value, we won't detect anything. The prevention story still works the same way.
Right.
But the detection story, if everybody, if this thread actually wrote a 0 in here instead of a 1, we're just comparing the contents. And so if the contents haven't changed, we assume that nothing has happened.
Could you detect it by saying, oh, that process had to do a copy on write, so something must have changed?
So what we actually do is, because that's too coarse of a grain, unfortunately, because it's a whole page. So what we do, in fact, is we actually don't delay until the end. We don't wait for the end of the week. We do this every 10 milliseconds. So every 10 milliseconds, you do a check. And we use this for two reasons. One, to detect things that change and change back. But two, more importantly, to find things that are false sharing examples that matter. Right? If I do this one time, who cares? Right? I don't want to report this. This would be crazy if I only did this one time. Right? Because I had one invalidation for a week. Don't care. Okay? But if I have millions of invalidations over a week, then we're talking something real. So what we do essentially is sample it by comparing these results over and over and over again at these intervals.
How long does it take to do the comparison, roughly?
I mean, it's all based
Yes,
on the number of pages modified. Yeah, and it just does a quick mem compare.
Yeah.
So
do you sample on a regular basis, or are you trying to make it a little more random to?
that's a good question. I mean, in reality, you should do things randomly. Right now, it's regular. Yeah. I think random sampling is actually the only way to go where you can get a provable result out. But regular sampling works pretty well too. But you're right. We should actually choose them. Okay. So basically, that's the story in terms of the mechanism. So of course, there's complexities. There are some other details I've elided. One key detail is that we also hijack the memory allocator, so that we know things about the memory allocator. We deliberately segregate all objects from the same call site into the same set of pages. So this means whenever we get false sharing on a page, we know that it's from objects drawn from the same call sites. So this allows us to actually identify heap objects by call sites trivially. And like I said, it identifies globals by name through ordinary sort of ELF tracking. All right. So performance overhead. So yeah, like I said, it's going to be breezy and quick, but that's OK. So this is a collection of two benchmark suites. One is called Phoenix. The other is called PARSEC. The PARSEC benchmarks are bigger. Phoenix is essentially they're programs that were meant to show the value of this map reduce for multicore. So it's a bunch of these little programs, and then these are a bunch of big programs specifically designed to exercise multicore in complex ways. So the black bar, this is on 8 cores. The black bar is with pthreads. The yellowish bar, which is supposed to be green, is the runtime of Sheriff in the prevention mode. And the red bar is with detection. So there's added overhead for sampling, which slows things down a bit. The interesting things to see, so first you see that the geometric mean overhead is very low. But this includes one pretty big improvement. The pretty big improvement is this benchmark called linear regression. So I should add, we found false sharing in a number of programs. Here's one, right? So if you see that it goes faster, there's false sharing. Here, things went really fast. So this sped up by, I think, 11x, which is a lot. And so just the act of using Sheriff fixes the problem. But we then used the detection thing, and it turns out that they were mallocing an object, basically a chunk of memory, and then parceling it out to each thread. And then every thread was updating those pieces. So they had no idea. I just communicated this to Christos Kozarakis, who's the head of the project at Stanford, and said, hey, you have this false sharing problem, and sent them the code. So one-line fix. So just malloc the objects separately, and with some padding, and then you're good. You can also just increase the size of the struct that they were sharing. Throw in 64 bytes, and you also dramatically improve performance. And so the performance you get once you fix it is a little bit faster than the performance that you get with Sheriff. I think Sheriff's improvement is actually on the order of 9x, and then when you just change the code, it's 11x. So not using Sheriff is even better than using Sheriff in that case. So that's basically it. We are killed here in Ferret, but killed relative to a tool that takes 200x I'm not too upset, right? But as a runtime system, you probably don't want to slow your program down by a factor of 4. What's happening in Ferret is that Ferret has tons of critical sections, which is probably a bad thing, in fact, because it's acquiring and releasing locks over and over and over again. But that's particularly expensive for Sheriff, because what Sheriff has to do at the start of any transaction boundary is protect all memory, say it's all read-only, which means a system call, it means updating the TLB, and then you take protection faults for any updates. And so for a lock, there's for sure going to be some update, almost certainly. And then the locks that we use are cross-process locks, which are also more expensive. So you can see, although not that bad. Linux is, I wish there was, well, there's an OS person over here. Windows is very, very inefficient in a number of regards, and its locking is very, very, very slow. And Linux has these things called futexes, which essentially in the fast path do nothing more than an atomic check. Even though you're doing, so it avoids a kernel crossing, which is good. Yeah. All right, so I hope you're convinced by the performance results and the mechanism stuff. Let me give you a few caveats.
I have to say, I'm really surprised by the low overhead. I mean, it
Yep.
seems like
It's awesome,
that
right?
these things don't do much locking and unlocking at all. Is that? I mean, almost all. I mean, yeah,
They
almost
do
all
locking,
these-
right? It's a question of how frequently they do it,
Right.
right? So, basically, there's this big, giant pain that you take when you acquire a lock. But if you then do a bunch of computation outside of the lock or in the lock, which would be
Right.
stupid,
Right.
you amortize the cost of the pain.
But you know that. Well, okay. It's just an interesting result. Is it a reflection that there's a lot of? I mean, most of these programs are highly unshared to begin with. In other words,
Well,
they to be scalable, they can't.
That's right.
Have much lock contentions.
Yeah, I mean, this is really like, excuse me, these programs were designed to scale, right? They weren't written by idiots. They're written by Stanford and Princeton grad students. Well, you draw your own conclusions. No, I think they're all perfectly capable people. I know that they recently discovered a race in one of the PARSEC benchmarks, and we discovered a race that we've not communicated to them yet, but these things happen, right? But in terms of performance, they tend to scale pretty well. So they've got that part down. The linear regression story, they have results in the Phoenix paper, and it's like, wow, Phoenix kills linear regression. Not when you get rid of the false sharing. So the map reduce thing looks great for linear regression. If you go back and put this result in, then that advantage goes away. And it was one of their big wins. Yeah. Yes?
So we can fix linear regression by adding some padding or something
Yes.
else. But when somebody just increases the cache line size,
Yeah.
it's all dead.
That's right.
So do you mean that basically we have to run Sheriff all the time, or just change the way we do things?
Well, I don't know about change the way we do things. It would be great, right, if we could run Sheriff all the time. I would like to get this to run faster. We have ideas on doing this. One of the things about Sheriff is that the cache line size is just a parameter. It's a runtime parameter. So you can easily sort of future-proof your programs by running it with Sheriff and doing false sharing detection for 256, 512. That's just how much it actually checks for false sharing. So I think that probably makes more sense from a practical point of view, right? Use this to say, all right, I'm gonna make sure that there's no false sharing when Intel comes out with its Jumanji processor that has 1,024 byte cache lines for some reason. Yeah.
I don't know. If you think about it, right, the argument you're making along the lines of, the overhead is so low in some of these, right, and it does kind of make sense. The more scalable the program is, the less it's going to be doing locking and unlocking to begin with. The less overhead you're going to have, right? So you're like, there's no reason. I mean, if you're string match or word count or whatever, there's almost no reason not to run.
Well, there are two things. So there's the lock stuff. The other issue is, it basically is the size of these transaction regions in the end.
Yeah.
All right. So if I go and I touch a whole bunch of pages very, very sparsely, that will kill Sheriff because it'll incur a page fault for every one of those. And the comparison phase is actually, right now, it's serialized. So the comparison phase is it goes and it scans all those pages looking for diffs, for the detection. And for the commit, it still has to go through all the pages and compare to see what it's going to write. So that stuff we could parallelize, and that would, I believe that's actually the problem in reverse index. That the problem is not the locks, but it's tons and tons of strings, and that's what kills us.
That particular operation.
Yeah, it's certainly embarrassingly parallel, no doubt about that. Yeah, I mean, one of the things, so the student on this, Tong Ping, said to me, hey, we can parallelize this because they're all multiple processes. Let's just do multiple threads in the processes to do this. And I was like, stop. I want to get this actually published because I want it to work first. So I said, we'll tune it a little more. The results are still pretty good. Yeah.
So the follow-up from my question would be, can you think about some improvements in the current, say, operating system services or hardware services which will help us somehow out of the fault sharing business altogether?
Right. So, I mean, there have been hardware proposals. It's been a while. Actually, Doug Berger wrote a paper many years ago, who's here at MSR, about dealing with fault sharing and making it cheaper, essentially moving around diffs. So there's something you could do. I think one of the more interesting questions is if you believe that the future is pointed to by this new Intel processor, this prototype that has no cache coherence. So you have every core has its own memory, and then you commit to there's a shared bus, but there's no cache coherence across them. Cache coherence is a problem. It's always been a problem for scaling SMPs. It's certain to become a problem if we really insist on going up to gigantic numbers of cores. One of the cool things about Sheriff is that you actually don't need cache coherence at all, right? It doesn't rely on cache coherence. Everything is a separate process. So this, in effect, puts cache coherence in for you pretty cheaply. So if you had no cache coherence, this would perform the same. I don't think the pthreads versions would perform as well. So that's an interesting question. We were thinking about, part of the problem I have writing papers on this topic is that if, say I have this great mechanism. Look, it's a great mechanism. It's good for this. That's a whole paper. It's also good for this. That can't possibly be a whole paper. I mean, for me, it seems wrong, right? Oh yeah, just use this mechanism. Look how awesome it is. I don't know. Maybe I should be more LPU focused. I can't imagine.
Would
right.
having mechanisms that were finer grained than the page size, like you had a cache line size way to detect or set protections and things, would that be helpful?
Yeah. I mean, finer grain obviously is always helpful. The problem with finer grain obviously is you have to store that information somewhere. If you make everything fine grained, then it's impossible. So of course there's the Mondrian stuff, which does it sort of adaptively and does it for different sizes. But if you make everything fine grained, you're stuck. You have to have bookkeeping.
So there's some results that basically you can use, like you can use ECC bits. I mean, there's very same tricks.
Sure. Yeah. That's a great paper.
Well, I was going to say, and that's with stock hardware. You imagine
yeah.
just putting the same mechanism into the hardware directly.
Yeah, of course. So that paper, which I think is called SafeMem, it's by YY Zhou. It's woefully undercited. It's a very clever trick to use the ECC bit to steal the bit and basically just get some sort of memory safety out of it. Very, very clever. I highly recommend you read it. I don't know how you would use it in this context, right? In their context, they deliberately flip the ECC bits so that you get an ECC complaint. And that's this kind of low-level, it's a very lightweight interrupt. But it doesn't have anything to say about threads and thread sharing. So.
Could you imagine a language level? So, in C, you have volatile that says stick this in a register. Could you imagine something that says stick this in a separate
It says the opposite. Volatile does. But yeah. Right.
Sorry.
Yeah.
Right. But I mean,
I know you know this.
Could you annotate variables and say, look, I know these are going to be divvied out to a bunch of threads. Make sure that they don't, so that we don't have to constantly chasing the next cache line size panic.
Right. I've not really considered it. I mean, I know, the way that people get around this right now is they align things. So there are pragmas or decal spec things that you can do in G++ and in VC++ that allow you to say, I want this to be aligned at a certain boundary. And that's useful for SSE things, but it's also useful for preventing false sharing. So you can tell a field, I want this field to be aligned at this boundary, this field to be aligned at this boundary, but it doesn't really, this does not address your concern about being future-proof. It seems reasonable enough to say, right, I want to declare some sort of conflict. I want to say this field and this field are going to be shared. But on the other hand, we could probably do some of this with static analysis. Right? I mean, certainly we could have thread-aware static analyses that actually look at sharing patterns. The challenge is coming up with false sharing things that matter. And I think that some of this stuff that Sumit has done on speed that allows you to figure out how often certain chunks of code are running, that might actually be useful as a way to weigh the importance of these interleavings.
Does this work for stuff like Java runtime and such?
So this is all a C story. Would it work with the Java runtime? I mean, I have to imagine it would immediately crash because it's such a gigantic mess. Yeah, I'm not sure it would help much, even if it did work, because it would only discover things that are happening at the Java runtime level. You'd have to expose the heap. You really need to expose the Java heap. It needs to be aware of what objects are what. You'd have to connect it up with the garbage collector. So you couldn't just plug it in.
Plug it in, it will put the garbage collector to a separate process.
Maybe that's where it should be. Yeah, that part doesn't really matter, right? It'll still work.
Yeah, sure.
But the real problem is that it could report tons of false sharing. So you think of the nursery, for example. If you're doing a nursery and you're allocating objects and you're constantly recycling the same buffer of memory, all of those things would be considered, well, potentially could be. Let me take that back. In fact, most Java runtimes nowadays have per thread nurseries. So actually, that would be OK. So it's only when you do a collection. But you're definitely going to collect the same regions of memory. It's going to discover things, and it's going to say false sharing.
So you would need an entirely different technique for, say, the Java runtime?
I think you'd have to do a lot more engineering. It would be much more intrusive because Java is this monolith of stuff. And to get in Edgewise, I think you'd have to actually put in hooks into the garbage collector at minimum.
Probably can generalize that to arbitrary VMs, whether they're language VMs or virtual machine monitors or whatever, where you've got this abstraction layer between the heaps that you care about and the heaps that the system sees, where there's this translation bit in between.
Right,
and
right.
So
I mean, your point basically is as soon as you have some extra thing hiding what a heap is from anything lying below, you would have to get in Edgewise and put in some plumbing. I'm not going to do that. All right. Cool. So that's the end. So there's Sheriff, right? So detection, prevention, reasonable performance, and you can barely see Darth Sidious, but we want to get rid of the insidious false sharing. All right. Anyway, thanks for coming.